right, so far we've been talking about what happens to momentum when there is no external force. And so we've always been saying that F was equal to 0, and then that would means that delta P is equal to 0, so that the momentum you begin with has to equal the momentum that you end with. Now what we want to do is talk about what happens if F is not equal to 0. So I'm going to take my delta T over to the other side, and I'm going to say F times delta T is going to be equal to delta P. Now normally when you're using a stopwatch, the initial time is going to be 0. So that means that the change in time is just going to be your final time. So we could actually get rid of the delta thing here and say that this is just F times T is equal to the change in momentum. So in our previous segments, this side over here was 0, and then that meant that your initial momentum had to equal your final momentum. This time, momentum is not going to be conserved. So this time, the initial momentum is not going to be the same as the final momentum because there's going to be an outside force acting on the system. And so an example of this would be a baseball player. So that you have the ball, the baseball, so that's going to be the system, is initially going in this direction, and then the batter has the bat, and then when they hit the ball, now the ball is going in this direction. So the momentum has been changed. Now, let's say that the batter misses the ball. So he swings at the ball and he misses. Well, then he doesn't exert a force on the ball. And so what does the ball do? Well, the ball just keeps on moving with whatever speed it had over here in this direction. So notice its momentum did not change. So if you don't exert a force on it, the momentum does not change, but because he did exert a force, he changed the momentum of the ball, and now it's going in this direction over here. Well, before we go and solve a problem like this, I did want to point out that this quantity right here, force multiplied by the amount of time that the force is acting on it, is going to be called an impulse. And it has its own special letter called J. And if you're one of my students, don't worry about it. Okay, so don't worry about the J thing. Okay, but you should understand what an impulse is. So an impulse is going to be the force that you apply and the amount of time it took you to apply the force. And then what an impulse does is it changes the momentum of the system. So that's important. So you should know what an impulse is, and you should be able to calculate with it. So let's take a look at a word problem here. A force of 6 newtons acts on a 3 kilogram object for 10 seconds. What was the object's change in momentum? Okay, so let's write down all the stuff that we're given. 6 newtons. Newton is a unit of force, so F equals 6 newtons. It's a 3 kilogram object, so that's mass. Kilograms is mass. It acts on it for 10 seconds, so that's time. And we want to know what's the change in momentum. Momentum is P. Now notice we don't want to know what the momentum is. We want to know what the change in momentum is. So delta P. All right, now what's the formula that connects all of these letters together? So it's going to be this one here. And so we're going to say force multiplied by time equals the change in momentum. The force is 6. The time is 10. So 6 times 10 is 60. So the change in momentum is going to be 60 Newton seconds. Okay, part B. What is the change in its velocity? So now we know what its change in momentum is. What would be its change in velocity? So we're going to use the fact that momentum is equal to mv. So the change in momentum has to be the change in mv. But if mass is not changing, we could take the m and we could put it outside of the triangle. And so this would be equal to m triangle v. So previously we took the m and we put it inside the triangle, but we can also take it outside the triangle. So the change in momentum is going to be equal to the mass times the change in velocity. Well, we know what the change in momentum is, that's the 60. We know what the mass is, that's going to be 3. And so solve it for delta v and you get 20 meters per second. So these are pretty easy questions that I think that you ought to be able to do on the exam. But then there's harder ones. So I would not expect you to be able to do this on the exam. But I went ahead and did it just to show you the power of this formula here. So estimate the force exerted on the bat by a baseball player when they hit a home run. So first I went to the internet and I found out that the mass of a baseball is 0.145 kilograms. Okay, then I found out what is the speed of a fastball. So I assumed a 100 mile per hour fastball. So the ball is initially going in this direction towards the batter with a speed of 100 meters per second. And notice I used negative 100 meters per second because it's going this way. And so that turns out to be negative 44.7 meters per second. Okay, then I found on the internet a video of a baseball player hitting a home run. And so the distance to the outfield wall for this particular stadium was 370 feet, which turns out to be 113 meters. And then, as soon as they hit the ball, I used a stopwatch to determine how long did it take the ball to get over the fence, and it turned out to be 4.73 seconds. And then I also looked up on the internet how long is the baseball in contact with the bat. So notice it's not what you might think. So you might have thought, well, maybe a second. Well, it's really 0.0007 seconds. So that's how long a baseball is physically in contact with a bat. Now let's take all of this information and plug it into this formula up here. So first we're going to calculate what is the speed of the baseball when it's going to the outfield wall. So it's got to be the distance to the outfield wall divided by the time it took in the flight to get out there. And so that's 113 meters divided by 4.73 seconds, and that turns out to be 23.9 meters per second. All right, now we're ready to use this formula here. Now we don't know what the force of the bat on the ball is, but we do know the time of contact was 0.0007. And then the momentum that the ball had finally, that's when it's going in this direction, minus the momentum it had when it was going this direction. And so it turns out to be 14,200 newtons. That's what I calculated it to be. And then I went to the internet and it says that it ought to be about 31,000 newtons. Well, when you take into account all of the different estimates that I was putting into my calculations, it's not bad that I ended up with 14,200 newtons. But that's an example of how you could use this impulse in order to solve an actual problem. All right, so if you want to pause me, blow up these pictures, these are some examples of momentum problems that I found out of Hewitt's workbook that you can do. So let's take one more break, and when we come back, we will do our lesson quiz.